is by looking directly at the CMB, doing models, trying to fit all of this information to fill these 6 parameters that I'm stuck about. So I won't talk too much more about that. Okay, so we have at least 3 sets of evidence now for dark energy. Okay, so we've got our supernova, we've got the baryon acoustic oscillations, and the CMB. So that's kind of reassuring that when we're throwing around terms like dark energy, that there is some solid evidence for why we think that there needs to be this dark energy that we don't know what it actually is. And not only that, we're really working very hard to try and understand the next steps, to try and understand a lot more about this dark energy. So, for example, I said that in Einstein's equations we have this as a constant, but it seems a little bit strange, maybe, that why would it be constant in time? Why would it be constant in space? We know that, for example, the gravitational pull of, is it going to change in a really, really dense region, or is it going to change in a really, really massive cluster? So we need to try and understand a little bit more about this. Is it going to change from the early universe until today? The strength of this dark energy. So we have lots of observations underway, EVOS and DESI, for example, and Pedro mentioned that Euclid and SKA, Square Kilometre Array, in South Africa and Australia, are also going to contribute to this, maybe on slightly longer timescales. But the point is that there are many, many observations that are now underway to try and really constrain this information and try and pin down what is missing in terms of our knowledge. So not only that, not only are we working on the observations, we're also working on simulations. So far the observations haven't given us any strong evidence that it's not a constant. But that doesn't mean that the theorists are going, okay, well, let's just use these constant models and go with that. There are many simulations that are being carried out to explore alternatives, many theories, new theories always being proposed, that we then need to test against current observations to see if they're consistent. Unfortunately, many of the theories that have been proposed have been ruled out based on the observations that already exist. We're still working to find more and more. Even though we are slowly beginning to understand, first off, we found that there is a need for something called dark energy, which was quite an achievement, given it's not something you would naturally think. And now we have all these new missions underway to try and understand it. And Planck has also been, which is one of the satellites that Karen spoke about, has been really good at helping with this task. But we do still have this big question of what is dark energy, and it doesn't look like in the next, well, in my generation of scientists, that unless we come up with some really, really exciting new ideas, we need people to really be working on this, and people are, but it's still, we're still kind of falling short and don't necessarily know yet. But hopefully we'll, by asking all these questions, by doing more experiments, we will be able to get there. Okay, so now we're on to dark matter. So this, well, let's start by, so what is dark matter? It's something, so dark matter doesn't interact with light, okay? You might, so I don't emit light, but I interact with light, right? You can see me because the light is reflecting off me and bouncing back in it. So you can see that I'm standing here. You can also see other, so air, maybe you say, oh, we can see through air, but at some wavelength you can't, or you've got different, you can heat up the air and then get different emission lines. So even these things that we don't necessarily think of as, oh, well, we can't see that, these are not what we're referring to as dark matter, okay? So dark matter, so I've started off with what dark matter is not. It's everything that we interact with, okay? It's planets, dust, everything that we see in our solar system, stars, black holes, gas, anything that we can see in our galaxy or in other galaxies, or any of the gas that we can see between galaxies. So all of this stuff adds up to being ordinary matter, and that adds up to only 15% of the matter in the universe. So that means that we've got 85% of the matter that is dark. So we can't see it. How do we know it's there? We have quite a lot of evidence for dark matter at this stage. So I've chosen a few examples of things to kind of focus on. Okay, so the first thing we're going to start with is our galaxy rotation curves. Okay, so this is the idea. So if you see a spiral galaxy, the spiral arms of that galaxy rotate. So the stars in the galaxy are rotating around. So we can observe this, which is great. We can also describe this motion using simple mechanics. Okay, so the rotational velocity of the galaxy is proportional to the mass divided by the radius. So basically, what that means is, let's look at the plot first. Okay, so in here we're going to have some mass. So the mass enclosed, we're going to imagine drawing a circle around the center, and then draw a slightly larger circle, and a larger circle again, and inside each of these circles we're going to measure how much mass is in that galaxy, okay, or how much mass is within that circle. We're going to assume that all of the mass that we can see is in the light, okay? So that means that the mass just corresponds to the light. So as you go further out and out and out into the galaxy, you have less and less, you're accumulating less and less mass. Okay. So what that means for our relation, in the center, we're increasing in mass as we go out, because there's still quite a lot of mass in the center. And then as we kind of reach the outskirts of the galaxy, the mass is staying reasonably constant, but the radius is increasing, so we get this fall off. Okay. But what we observe is not that at all. We don't see this fall off. We don't see this the velocity or the speed at which the stars are rotating. We don't see that they slow down in the outskirts. What we actually see is that this white line here. Okay, so they're reasonably this line corresponds to constant, so they're reasonably constant. So what a constant line here will tell you. Okay, so let's say this is equal to 1. That would mean that the mass, as you increase in radius, you have to increase your mass. If you're going to keep this value at 1 as you keep going along the scale. So what that tells us is that there must be more mass in here than what we see. Okay? So that's quite interesting. We might say, oh, well, maybe it's gas. But we can observe quite a lot of, we can attempt to observe and account for the gas that's in the galaxy. By using different observations, different observational techniques that don't just look at the optical, and that don't just look at the light, this type of light. For example, in X-rays, very, very hot gas emits an X-ray, so that tells us something about that. But basically what we find then is that there's something missing. There's quite a lot of something missing. So we need to have some way of accounting for this. We know there's something there. We don't know what it is. We can't directly see it. So we call it dark matter. Okay? So this is one of the ways in which we can detect it. Another thing is gravitational lensing. So Haranya talked about the lensing of the CMB. This is slightly different. So this is galaxy-galaxy lensing. Okay, so there's no CMB photons involved, just galaxy photons. So if I have first off, let's talk about, Petra talked about space-time. You imagine this blanket or a sheet, and then you put a ball in the middle of it, and it bends the sheet. Okay, you can, and if you throw another object into this sheet, it will spiral around and fall in towards the center of that galaxy. With light, what happens is instead of traveling in a straight line, the light, in fact, is going to follow what the sheet does. Okay, so the light can be bent around the object. What this results in is basically a lens. So you get something like this, where so this is just a wine glass on top of a simple, okay, quite a simple experiment. You can do it at home. So what happens is that the light from that's reflecting off this sheet of paper is coming through this lens, but the light can't travel in a straight line through the lens because it's not just a plain piece of glass. So that results in this bending, and you get this slight deformation, basically, of the grid. So we see the same thing with we can see the same thing when we look at big galaxy clusters. So you need to be looking at a very, very massive object. So what a galaxy cluster is just a group of galaxies all in one place that are usually bound gravitationally. So what we have is you've got your galaxy cluster, and you've got some small background galaxy. It doesn't have to be very big, just has to have some amount of light, because that's going to be magnified by my lens. Okay? So the light from this galaxy is going to travel along space-time, it's going to bend around the object, and then come out the front. So even though it was somewhere behind, you can still see it in front because of this lensing effect. So, so you can think about it just like a regular lens. And then what we get, so if the object is directly, if two objects are directly aligned, then you get this very perfect, what's called an Einstein ring. But we don't typically see that because galaxies are not perfectly in the universe. So, but what we do get is we get these weird galaxies, right? So you see along here, highlighting the next slide. So you see along here, there's all these kind of very, very long, elongated, distorted looking galaxies. So these are what we see. And that's evidence that this space-time is causing this distortion of the galaxies. And you can look at things like the redshift of the galaxy, and it tells you that it's much further away than all of the galaxies in the center. But then in terms of dark energy, we understand reasonably well how to produce these images. And we can measure reasonably well all of the mass that's coming from the stars, from the light that's shining in this area. But when we plug this into the models, it doesn't work. These galaxies do not have enough mass. They don't bend space-time enough to create the images that we're seeing here. Okay? So again, this is telling us that we have some missing mass in the universe. Oh, there we go. Okay, so some missing mass. So maybe you could think of some nice way of explaining the rotation curves. Maybe you say, oh, maybe something's a little bit off there, and maybe they didn't do their calculations quite right, maybe they needed to account for this. But whatever you use there, you then have to also use here to explain this. So as you accumulate more and more evidence for this dark matter, you need to find a consistent theory that explains all of this evidence, and it becomes more and more complicated. Another example that we have is the bullet cluster. So I'm going to go through this reasonably quickly, but in blue we have the dark matter, in red we have gas. These are two galaxies that have collided. Okay, so this is one and this is the other. Okay, and when we look in X-rays, we see hot gas. When we look in the X-rays, we get this nice red plume here. When we look at the gravitational lensing maps, like what we saw previously, how the gravitational lensing works, we get these two blue blobs here. Okay, so that tells us that so there's an offset between where most of the mass is and where all of the gas is. And this tells us that whatever is causing this lensing, whatever is causing all of the mass to be considered to be here, is not gas. It's not ordinary matter. It's not interacting in the way that we expect ordinary matter to interact. Okay, so we can also go on and we can start asking more complicated questions. We can start including these, including some of these theories of dark matter into simulations. And depending on the type of dark matter that we include, we can get either very, very fine-grained structures in the universe, or we can get much, much smoother structures in the universe. So through then applying our knowledge of dark matter, the restraints that we put on, we can, as astrophysicists, we can then go and use these to try and understand what's going on, or understand the actual nature of dark matter. But there's another side to this, okay? So I've spoken about the evidence for dark matter, but of course, if this is matter, we have to ask, well, what is the matter? What is the matter? The matter is we don't know. So what is it that's making up all of this extra mass in the universe? So the particle physicists have been working, find this an equally interesting problem as astrophysicists. So they have huge teams of people trying to understand this. So you have something like a standard model. I don't want to go into the details of this, but perhaps you're familiar with the standard model, which makes up all of the ordinary matter we know. And then we try and add extra things. Maybe there are sterile neutrinos. Maybe there are more massive neutrinos than the ones that exist in the standard model. Or maybe there's weakly interacting massive particles that we nickname WIMPs, which which as they pass through most material, they don't interact, the weakly, but on some small occasions they can interact. On some specific occasions they can interact. And then the other thing that you can have is supersymmetrical particles, which is really going to work. There's basically a whole other category of the standard model that are symmetrical to what's found in the standard model, but more massive. There we go. Yes, so you get these extra particles, basically. And all of these theories exist, and they're now being tested quite a lot by many different experiments, and there's different teams working on testing these different theories in the same way that different theorist groups are working on coming up with the theories. So some examples of the tests are at CERN. They're looking to detect the supersymmetrical particles, so this extra set of particles. They're hoping to generate some of them in their next set of tests. There's also experiments looking for WIMPs, so they use so basically they use big vats of heavy elements and leave them in a mine somewhere. There was an active experiment in the northeast of England doing this, actually in one of the old coal mines until quite recently, and they looked to see if they noticed any unusual activity in these big vats of heavy elements. And so far, so what this plot is just showing is how strong an interaction you need versus the mass of this theoretical particle. And basically everything above this blue line has been ruled out. So we're running out of space to see what's next. Another maybe less obvious experimental environment is the center of our own Milky Way. Okay, so this is a really extreme environment, and so that makes it quite an interesting thing an interesting place to look. And what we look for is just some slight signal that we don't expect, basically. And what I mean by a slight signal, so we expect, in this bottom panel here, we expect these blue dots, and we see these red dots. And that's a tentative detection, okay? So what we see, basically, is there's this extra line in the spectrum, or this extra wavelength where we see a spike, and we can't explain that. And we think, maybe this is interacting dark matter. So a lot more experiments are underway, and we'll continue to, if not find dark matter, at least rule out the current theories, which is, yeah. So although we don't know what dark matter is, we do have very compelling evidence. And to explain all of the observations that we have with a single theory that is not dark matter is proving increasingly difficult, okay? To the point where most physicists, most astrophysicists now are quite happy to assume that there's some need for something like dark matter. But there are still some minor things that dark matter has to explain, or in particular, the details of the dark matter need to be ironed out quite a lot. So, where does that bring us to? We now have our dark energy and our dark matter accumulation. Okay, so we start at the CMB. We have Einstein's equations that explain to us how we evolved to the present day, and then what happens. So we've got the dark energy and the expansion of space reduces how much structures can collapse, because you're increasing the distance between particles. And as we, if we just think of a simplified version of general relativity, such as Newton's equations, you've got, if you have two particles, they'll be brought together due to their mass. So the expansion of space causes them to move further apart. But dark matter significantly increases that pull. Okay, so you've now got, instead of the 15% ordinary matter, you've got this other 85% matter that although we can't see it, it still acts through gravity. Okay, so we've got the initial density fluctuations in the CMB, so these little hot and cold spots. They grow. We find that the high density material, the high densities grow. The high densities attract more material, and the low densities lose material to these higher density regions. So it amplifies these differences. And then you end up with a structure that looks like this. Okay, so this is a simulation of just matter. The yellow bits are high density, so this is the areas where galaxies will form. And then you can zoom in, and you see that when you begin, it's quite a uniform structure. And then as you zoom in, you start seeing this this web-like network that moves towards where all of the webs are interacting at these little nodes. And in these nodes, you'd find clusters of galaxies. So the Milky Way would probably live in a halo something around that size down there. So not the central size, but one of these smaller halos. So then we can then try and connect these models to gas. So what this is showing is a time evolution of a simulation. So this is showing you the dark matter structure. So then filaments, that web-like network, you can see it start to form. So you start with everything looking pretty uniform, and then you see these web-like things start to form. We zoom in on a little galaxy. So this is a galaxy that will be about the same size as the Milky Way when it ends. And we look at the gas, okay? And this is quite exciting, right? So gravity is pulling all of this material together, but then there's interactions from the gas that result in a slightly puffy element to it. And then you form a disk, and then you can look at the stars in the disk. And then that will continue to evolve up until the present day. And you see that there's quite a lot going on in each of these. So to try and understand the formation of the Milky Way, we need to look at systems like this that are embedded inside this structure that describes how the dark energy and the dark matter should result in evolution of the universe. And that is a simulation at redshift 0. Am I okay for time? Okay, let's skip through the movie. So let's skip that one. So then we can look. The specific simulation that I'm involved in is called Eagle, which is why it says Eagle all over the place. And so this simulation is one of the first simulations in a large that simulates a large area of the universe that includes the dark energy, the dark matter, and this extra component of gas and stars. Okay? So it's very computationally expensive. We ran this simulation for a month on 4,000 cores. So that's the equivalent of hooking up 4,000 laptops to try and get the simulation to run. And running it non-stop for a month. It was quite a feat to get done. But at the end, what you want to do is you want to see if the simulations that you produce, if the galaxies in them, not just this web-like structure and these dark matter blobs, if the actual galaxies in there look anyway similar to the galaxies in the real universe. And we've found that we've had very good success so far. So what we've done here is try and look at the different morphologies, so the different shapes of galaxies. So we wanted to see what types of shapes we get. So we get just very nondescript circular or spherical galaxies. We get things with maybe a little bulge in the center that extend outwards. This is maybe a little bit less bulgy, more extended. Then you get these big disc-like galaxies. So you've got a bulge or something that looks more like a bar in the center, and lots of structure going on in the outskirts. And you can kind of see some spiral arms happening here. And then you've got some weird morphologies as well that don't really fall under the kind of elliptical or disky-like galaxies. And in the real universe, so this is from Galaxy Zoo, you see something similar in terms of the shape. So you see these nice spherical galaxies, you see these barred galaxies, you see disky galaxies, and that's quite nice. It's quite reassuring. Okay, so these images obviously don't look exactly alike. I'm not going to try and convince you of that, but we're very, very close to understanding a lot of the structure or a lot of the structure formation that goes into galaxies. And to understand how galaxies form, we really need to know a lot about cosmology. So this is telling us that what we've worked out so far about our cosmology, about the dark energy, about the dark matter, about the requirement, about how much of them we need, it's telling you that we're getting there. We really are moving forward. Okay, and then I just to kind of put this in a little bit of context. this is a dark matter simulation, and this is where the galaxies live within that simulation. Okay? You'll see that there's a lot more going on over here than there is here. What we can actually see in the universe in terms of the galaxies is such a tiny, tiny fraction of what's actually out there, that the fact that we can go, that from observing these kind of structures, we've been able to determine what goes on here is really quite phenomenal. I think it's very impressive. And that so far the scientists have brought us this far forward. Okay, so do we understand everything? We understand a lot. We have an overarching theory of how structures form, of the things that we can see and can observe. But we don't fully understand the nature of them things. We don't fully understand the dark energy. We don't understand, and we're kind of maybe pushing the boundaries of trying to understand dark matter. We also have some issues with the gas physics, but that's minor by comparison to these two really, really big questions. So although we don't fully understand dark energy and dark matter, we call them dark and we don't know what's going on, hopefully I've given you a little insight as to why it is that we talk about these things, why it is we think that these are important, and that these are a crucial part of our framework for cosmology. So I'll just leave that up, take-home message. We've got dark energy. We know the universe is expanding and accelerating based on our observations. Dark matter, again, based on observations, there must be something there, and it seems to be consistent with the theories that we've developed in the simulations that we've done. And we can now, so we're now at a point where we can create these virtual realities, these universes in a simulation or in a computer, which is really quite cool. And we can now use that universe to try and test things about our own universe.